Welcome to the Energy Institute. Welcome to the technical webinar series. And in particular today, we are going to be focusing in on this recently published guidance. So it's got an EI number 3601, and the name of this guidance, Guidelines on Corrosion Management Asset Integrity for Wind Turbine Infrastructure. That's the one we're going to be covering today, but we'll do a little bit of introductions, etc., as to how we got to there, and then we'll let you know what we actually developed. How's that? Next slide, please. So first of all, before we get into the details, a little bit of the standard housekeeping. How does this work? First of all, to say the webinar's being recorded, and that's because we're going to make this available after the event. So that's the first thing. As a participant, you're going to be muted. The sound is only going to be available to the presenter, so I'll flag that. However, we're very keen to get your questions and answers. So if I move my mouse on my screen, there's a bottom bar, and I can see a little box that says Q&A. So type in your questions in there. If you can't see it, there's a little thing, a circle with 3 dots. It says more. The Q&A is in there for sure. All right. So all you do is you go in there, go into Q&A, and you can load up your question. So put them in there. Don't put them in the chat, but feel free to introduce yourself as well. So that's kind of the basics there. Key thing is we would welcome your questions when we finish the presentations. We're allowing plenty of time so we can explore what this guidance means to you. Perfect. Next slide, please. So let's do the introduction. The Energy Institute, you can see from this slide and from me that we are looking to cover the global industry. So this is creating a better energy future for our members and society by accelerating a just global transition to net zero. There it is. That is the big statement, the banner headline. Next slide, please. How do we do that? Well, first of all, who is the Energy Institute? Let's have a look at that. First of all, it's a chartered professional membership body for those who work across the world of energy. So it's the whole thing. If it's energy, we cover it. That's the idea. We're a registered charity. We date all the way back to 1914, and we're incorporated by Royal Charter. So as you'd expect with a chartering body, and we can award chartered engineer, chartered environmentalist, and chartered energy manager statuses. Okay, so as a chartered engineer, this is of value to me as an engineer in the industry, and I think on our call here we've got a number of chartered engineers as well. This is some numbers for you. We're looking at 20,000 individuals across the world, 200 companies, and working in 120 countries. So it's broad, we can safely say. It's a unique global interdisciplinary community working to create a better energy future. And that's a recurring theme. That is what we're looking to do, a better energy future. Next slide, please. Right, the triple role. Let's just cover that quickly. 3 sort of main areas to break that down in. 1, the workforce, attracting and developing is key, a diverse energy workforce. Then convening expertise and evidence to inform energy decision making. And you can see there's the UK Parliament building there, but this is again across multiple areas, disciplines, etc. Over there on the 3, enabling industry to make energy safer, more efficient, and lower carbon. And that's all tied in with the international drives for a low carbon economy. So that's the triple role. Next slide, please. And here is a snapshot of some of the people that we are working with actively to deliver all this. You can see it's quite extensive. You will probably, depending on your discipline, recognize some of these companies and some of the companies you might not, because I said all energy. Things like we're talking about asset integrity. Well, this goes all the way over to aircraft fuel and things like that. So, excuse me a second. Next slide, please. Great time for my voice to go. Anyway, here we are, the good bit. This is what we're focused on. Technical and Innovation Program. So this is us going from the big EI into the bit we're really focusing on today. We, as well as chartering, have a technical program. We look after this program, and you get that simply Energy Institute Publishing. Put that search in, you can come in and have a look at the sheer number of guidance documents and standards we have. So every year about 30 standards, good practice and authoritative trusted guidance is produced. We work across the breadth and depth of the global energy sector, from oil and gas to renewables, upstream, downstream, the whole thing. And what we're doing is helping to accelerate the energy transition through industry collaboration, dialogue with regulators, academia, and wider stakeholders. So we're bringing everybody in a collaborative way to address, as far as we can, everything for the energy sector. There you are. It's broad, but we are now narrowing it a bit further. Next slide, please. So this is my introduction here today. So we're looking at this guidance that was mentioned back at the top there. Here's your details, published August. There's your ISBN number, and it's a first edition. But let's now get into some introductions of who you're going to hear from today. So there's me. Hi, I'm Dr. Cameron Stewart. I'm the EIAAG manager. I'll explain that in a second. What we'll do is I'm going to do a short introduction, and then what I'll do is I'll hand over to the steering group chair for this piece of work, Alistair Crichton from Adura, who's on screen there. Alistair will give you a wee wave, I'm sure. And then what we'll do is we'll move in and hear from our specialist drafting consultants team. So that involves Intertek Capsys working with Apollo. And what they did is they helped the steering group take their ideas and helped us develop it into the full guidance. So that's the plan there. And what we'll do, and when I do that, I will hand over then to David to take us through the webinar. And then once we've gone through all of that, we will go to those questions at the end. So just a reminder before I go into my introduction, get those questions in as they occur to you is probably the best way to do it. And my key, most important message of all, enjoy the webinar. That would be it. Next slide, please. So an introduction from me. I've said AAG, you've seen it on a few of the slides. What does that mean? There in orange, that top box, you can see the AAG shortens quite a bit. Asset Integrity Management, or AIM, and Aging and Life Extension, or ALE, shorts to the primary A's and G for group. So there you are. That's put a long sentence down to a very short one, is what I would say there. Next down, next tier, you can see two boxes there, the Corrosion Management Asset Integrity Committee and the Age and Life Extension Committee. In honesty, those are mainly structures peoples. I would flag that. That's our two committees under that group. And the other one, down in your bottom right-hand corner, you'll see Met Ocean. That is actually a network, a global network, looking at everything on environmental loading. So you can think of wind and all the rest of it, but primarily, if you're in the sea, you're looking at wave loading. That's your key focus there. And extreme wave loading. That's the groups that work together on all these other boxes in the middle, and that is live or published work. And this is for wind energy. AAG is much beyond this. It is a much more complicated picture. I've restricted it purely to wind energy. Okay, so basically, just to use this as an example, if you, just hold there, just to use this as an example, we would say there is either a gap in understanding, or we need to recheck a classic issue and see if we can update knowledge, etc. We put that idea forward for funding. We get awarded funding. The two committees there then form steering groups to turn that idea into the guidance. So what the steering group will do is they start looking at the proposal, expand it out. Then we bring in our drafting consultants to help us turn that whole thing into the new guidance. Lots of checks and balances all the way across the process to make sure that what we get at the end is of value to the industry. That's the aim. And at the end, I will be checking that we actually succeeded that. That's the plan. Flagged there on the left, you can see there's a little box there. That's the guidance we are talking about today. So you can see, just to sort of summarize what you're looking at here, that one we'll focus on today. Let me start at the other side. So where Met Ocean's involved, you can see implications of loads, comparisons of loads with AWARE. These are very much looking at wave loading, 1,000-year wave cycles, all of that kind of good stuff, but focused then on floating structures. Move one column in, you can see that we're looking at life extension for offshore structures supporting turbines. That's from AILCOM. That's the structures side. So we looked at supporting structures. We did a position paper, and now we're working on floating wind turbines, the structures supporting them. And over here, the next column, you can see a position paper has led to looking at extreme environmental loading of all floating structures. And then the left column, where we are today, you can see we're going to talk about integrity of offshore wind turbines, which is published, our aim today, but we are already on the next one looking at the asset integrity of the turbine infrastructures for floating installations. So quite a comprehensive coverage. And as I say, this is just the wind bit. All right. Next slide, please. So that's my introduction to sort of get us going, tell you what EI is, all the way into what the Technical and Innovation Programme is, all the way through to what is this guidance. That's where it belongs. That's how we got there. To start off our presentation today properly, I'd like to invite a few words from our chair, Alistair Crichton from Adura, who took us through this process in a most wonderful way, I have to say, in all honesty. Over to yourself, Alistair, if you'd like to say a few words.
Okay, good morning, everyone. Just a few words. It has been a tremendously enjoyable exercise in leading this or chairing this group. But just to reiterate something that Cameron touched on, the UN Race for Zero campaign challenges nations to reach or aim for net zero by 2050. The Energy Institute, as one of the previous slides intimated, augments that with their own asset integrity and climate resilience in energy, with a date of 2030 as the ideal strategy point. With regard to renewables, research and development into renewables is well established and ongoing, and indeed we have currently some industrial scale renewable activities ongoing. But with particular reference to wind turbines, they do contribute electricity to the UK grid, and indeed this has been the case since 2000 or so, with the UK Blythe offshore wind farm. Onshore wind farms have been in existence for a little bit longer. But when you look at, and this comes to the crux of asset integrity, and I apologise if this appears to be UK centric. We have, as Cameron said, this is multinational, so the expectations of the Health and Safety at Work Act 1974, which is principal UK legislation, is pretty much echoed across the world. Within that, and within the daughter legislation, material degradation or corrosion represents an implicit hazard to health and safety, and the regulatory expectation is that we should aim to have these hazards at as low as practically possible ALARP level. This document, the Guidelines on Corrosion Management and Asset Integrity of Wind Turbine Infrastructure, provides within the set parameters, which will be touched on shortly, both a review of the current technology and provides a reasonably comprehensive review of the material degradation faced by these offshore facilities. I will say something that as you can see on the right hand side, as you look at it of the slide, it was a sizable committee from a diverse industrial background. I started off with this committee when I was with Equinor. Equinor has a joint venture with Shell to become Adura. But as you can see, you have oil and gas companies, you have more focused companies more focused on wind energy, and so it was a really quite diverse group and a very enjoyable one to work with. Thank you.
That's fantastic, Alistair. Thank you very much. That sets the scene beautifully. Next slide, please. And you folks should be delighted. The last slide from me for a while is now for me to have the pleasure of introducing our drafting consultants team. They helped us draft this. Dr. David Bruxton is our lead consultant with contributions from Gareth and Paul. But what I'm going to do is I'm going to hand over to the guys now, and it's actually Gareth that's going to kick us off. So without further ado, Gareth, over to yourself. Let's hear about the guidance.
Thank you, Cameron. Thank you, Alistair, and good morning, everybody. Yes, guidelines on corrosion management and asset integrity for offshore wind turbine infrastructure, which is a very long sentence for basically how do we keep the windmills operating safely and ensuring durability going forward as we move through the energy transition. Next slide, please. As everybody is aware, offshore wind is an increasing source of power generation, both in the UK, but also worldwide. And as at the end of December, the offshore capacity is approximately 95 gigawatt, split nearly half in China, nearly a quarter in the UK, and an eighth in Germany, but spread across the world. And also at the end in December, UK broke its own record of the amount of electricity generated by wind, which was at the time about 50% of the UK total power generation. And there are current plans for a significant increase for such generation in the UK alone. And in fact, yet those who are based in the UK will be aware yesterday there was major announcement with regards to new licenses for offshore wind across the country, including both fixed wind and floating wind. And the graph here shows how the general capacity of wind has increased over the last 8 years or so, with again China taking the lead, and but then Europe following behind. And it was this global increase in capacity, coupled with known historical integrity issues associated with offshore wind, that was the catalyst for developing this new guideline document. Next slide, please. Now, fixed offshore wind covers a number of different structures, from monopiles to concrete structures to towers. But the scope of the document was to provide information and knowledge for the design and operation to ensure they are safe, reliable, and economic. And it covers both corrosion management and asset integrity management of offshore assets for fixed structures. But the document does not address onshore wind, nor does it address floating offshore assets. Though at the moment, as you will be obviously, the majority of the information in this document will be applicable to common features for both onshore and floating facilities. Next slide. In developing this document, we've drew on a wide range of expertise and resources, including our combined in-house relevant experience for offshore oil and gas, as well as our combined experience for existing fixed offshore wind assets, both monopiles and jackets. We also carried out a detailed lit search for relevant published papers, presentations on the topics, and incorporated them and interpreted them as appropriate. And also we used the steering group members, as was mentioned before by Alistair. It was a wide-ranging group with a lot of relevant experience, and we did, we did take as much of that into account as we could. We tried to cover the whole area of the life cycle, from development through to operation and decommissioning, and also mentioned relevant health and safety regulations. As Alistair mentioned, in the UK, this is under the UK Health and Safety at Work Act, but other areas as possible, but also incorporating comments on other regulatory issues from other areas. Next slide, please. Now, as most of the people here are, I'm sure, are aware, offshore wind covers a wide range of different structure types and different sizes. For fixed assets, which are the three on the left of the graphic, which are normally used in shallowish waters, i.e. up to around 60 meters or so. You have monopiles, which are normally used in the more shallow waters, jackets and suction caissons. But increasingly now there's a move to consider floating assets, which are used in deeper water, i.e. typically more than 100 meters, which include both semi-submersibles, spars, and other designs. As mentioned previously, the current document we're talking about today only addresses the fixed offshore wind assets. So that's monopiles, jackets, suction caissons, and the like. Offshore floating assets, as mentioned by Cameron previously, are now being considered, and there is a new EI document currently being developed by essentially the same team, and the aim is to get that ready for publication sometime in 27. Next slide, please. And this is where I pass over to Dave Buxton, who was leading the corrosion side of these things, to talk through the main areas of the document. Dave.
Okay, thanks, Gareth, and good morning to everyone. So I'm just going to briefly run through an overview of the corrosion issues that are covered in the document. And I think the first thing to say is the marine environment is a harsh environment. It's corrosive, especially to unprotected steel, and to ensure the continued safe operation of offshore assets, corrosion and the management of the corrosion is essential to ensure safe and effective operation. So it's generally the supply of oxygen to the steel surface that drives the corrosion, and then the presence of the chloride in the marine environment increases the corrosivity. And I'm going to run through the various corrosion zones, just briefly looking at the main corrosion prevention options and the areas affected and the sort of typical corrosion rates, and then just highlight a few issues that are included in the document. So if we start with the atmospheric zone, so this is above the splash zone, the higher levels of the structure. We're looking at the tower and transition piece and maybe the top parts of jacket legs and bracing. And its corrosion will occur where water phase is present on the surface. And the conditions can be aggressive. You've got a high time of wetness, so there's a lot of time for corrosion to occur. There's marine aerosols, you've got chlorides in the atmosphere, and there's the possibility of salts building up with time. So it's about the worst atmospheric conditions you can get. Don't forget about the inside, although there may be some degree of environmental control. Even the insides of the structures can suffer from corrosion. So it's needs to be considered the internal environments as well. So the main corrosion mitigation is protective coating and the inclusion of a corrosion allowance. Now, of course, it's only where this protective coating fails that corrosion will initiate. The protective coating, when it's intact, prevents the corrosion. External rates of corrosion for unprotected carbon steel in the most aggressive conditions could be up to 0.14 millimeters per year, as shown in the plot there. That's a 30-year average. The rates will tend to decrease with time, but over that 30 years, if that's your average rate, you are looking at about 4 millimeters of corrosion. So does need to be controlled. Another option for corrosion prevention is the use of CRAs, corrosion-resistant alloys, otherwise known as stainless steels, of course. I think the key thing here is it's important to select an appropriate grade with sufficient resistance. And the lower grades, I say stainless steel 304, that's EN 1.4841, that should not be used. And other grades with care in appropriate conditions after assessment. Just going back to the coating, it's a standard practice to apply coating, and there's guidance in various documents, including ISO and DNV documents. And the key issue with the durability of the coatings is the preparation and the selection of the right system. Next slide, please. And so this is an example of a standard coating that might be used for the atmospheric zone. A 3-coat system, zinc-rich primer, epoxy coat, and a polyurethane top coat, perhaps. And this is similar to the Norsok coating system 1A or 1B. The table shown on the slide is one taken from the document, and there's similar tables produced for each of the zones. So this is a standard. It could be modified perhaps by introducing thermally sprayed zinc as a first coat, or even using thermally sprayed aluminium with a sealer. And that would just be a sealer only. There have been some examples of thermally sprayed aluminium used and then overcoated, which has caused poor performance and problems. So the upgrades would probably be used for areas where perhaps they're highly inaccessible and you want the best durability coating as possible. Also, just to mention, in the document, we do cross-reference to a number of other EI documents, and there's an excellent reference for guidelines for management of coatings for external corrosion protection, and that's E3212. Next slide, please. Moving on to the splash zone. The splash zone is typically the zone with the highest corrosion rates, and that's largely because of high time of wetness. It's wet for most of the time, and there's still high oxygen availability. And the corrosion rates increase, and so you could have, say, 0.3 millimeters per year, but that does depend on climatic conditions. And the prevention options for this zone, again, coatings and possibly the use of thermally sprayed aluminium, more robust cladding or sheaths applied to the area, and the inclusion of a corrosion allowance. So if you could go to the next slide. And again, another example of a coating that might be applied. This is for the splash zone, and you'll see an increased thickness there, perhaps up to 1,000 microns, to provide resilience in this aggressive zone. And again, another EI document worth mentioning, guidelines for integrity management of the splash zone in offshore environments is a source of further information that can be valuable. Okay, so on to the next slide, and moving down to the submerged zone. Again, the corrosion prevention methods for the submerged zone include protective coatings, also cathodic protection. That's a standard measure to minimize corrosion, and the use of a corrosion allowance. And in the submerged zone, obviously, we're looking at the area below low water, which is continually wet. So it's the lower part of the foundation. The foundation and the lower part of the transition piece, and jacket legs if it's a jacket type structure. The corrosion rate will depend on the environmental conditions, to some extent temperature, again the rate of flow, because that affects the oxygen availability on the surface. If we could go to the next slide. Again, an example of the type of coating a two-pack epoxy system is often applied, with maybe a maximum thickness up to about 350 microns. The key thing for the submerged zone, the coating should have compatibility with cathodic protection. It should have good resistance to cathodic protection disbondment. And if that is the case, then the coating and the cathodic protection are complementary. The coating providing the primary barrier and covering the vast majority of the surface, and then the CP provides protection to those areas where the coating has become damaged either during installation or during service. And it makes for a more efficient, effective cathodic protection if you've got a coating in place. It reduces the amount of current that's required to achieve the required potential. And the cathodic protection system might either be an impressed current or a galvanic or sacrificial anode system. So next slide. So just to talk a little bit about the submerged zone and the cathodic protection that's applied. in this area because there were some issues with early designs. Many of the designs used galvanic anodes, and the outcome wasn't satisfactory. The design wasn't always adequate, and there were issues arising from the protection current density required. The design value that was assumed wasn't found to be sufficient in practice, and this was due to higher than expected seawater velocities around the structures. Secondly, there were issues with potential attenuation. So if you look at the diagrams to the right of the slide, the cluster at the near the top of the monopile is the anodes. These are mounted at the bottom of the transition piece, but you can see it's a long way down for the anodes to protect down through the foundation to this seabed level. And it was found that with these anodes clustered together at the top of the, or just below low water at the bottom of the transition piece, they weren't in a good position to distribute current effectively around the bare structure. There was a desire not to put anodes on the monopile foundation itself due to damage during installation. And then a further factor that caused issues and reduced the current output was this clustering of the anodes close together on the transition piece caused anode to anode interference. You can see in the picture at the bottom of the slide, the spacing between the anodes is fairly limited. It's maybe sort of 1 to 2 meters, and that reduces the output from individual anodes. And when that output is needed, particularly at the beginning of life, when high current density is required to polarize the structure, there wasn't sufficient current output. So I suppose a key point to note is that the application of traditional parameters based on, let's say, traditional experience on larger offshore oil and gas structures isn't a reliable approach, and new standards have been developed, ISO 24656 and the DNV RP 0416, which provide more detailed design guidance, and these should be followed, not the traditional documents. Again, another useful EI document that is referred to in the guidance we prepared is the CP offshore structure document that's mentioned there, EI 3036. Next slide. Thank you. So that's looking at the buried section. The corrosion rates are lower in the buried zone, down to maybe 0.01 to 0.04, and this is due to the stifling of the corrosion with time, lack of oxygen present in that environment. Maybe just one cautionary note: there is a risk of MIC in the top layer, maybe the top meter of the buried zone. But generally, that will be receiving some cathodic protection, and there are options for coating that small area that's at the interface between the seabed and the seawater. Next slide. So the another issue that arose in some of the early monopiles was the issue with the trapped seawater inside the monopile, and this is obviously a special case that just relates to monopiles. So you've got a local environment after the pile's been driven and the transition piece installed, with the trapped seawater. You've got some seabed mud at the bottom, and above the seawater, the airspace, the trapped air. The initial corrosion management strategy was to seal this whole environment, with the idea then that oxygen would oxygen levels would generally reduce because they'd be consumed by a small amount of corrosion, and then the corrosion rates would reduce to minimal levels. However, in many cases, this wasn't successful. There were leakages either through the cable entry J-tube. You can see at the bottom there, there's for the vast majority of monopiles, there'll be an exit point for the cable, the inter-array cable, and there's the possibility of that seal failing and then water exchange, or possibly through the transition piece to foundation seal. It's often filled with grout, but water can come through there. So there's the possibility of water exchange and oxygen coming in, or also oxygen ingress through the not so tight, airtight platform above. So there's direct air leakage into the headspace. So the revised strategy is now to allow exchange and to protect the internal of the monopile in a similar way to the external. And so that will be the measures previously mentioned, application of a coating, use of a corrosion allowance, and application of cathodic protection. But just a couple of warning points about the use of cathodic protection inside a monopile. There was some experience using retrofit aluminium anodes in some monopiles. This led to acidification of the seawater and the generation of hydrogen sulfide, which is a toxic gas. The approach now would tend to avoid the use of aluminium anodes, stick with zinc anodes or an impressed current system. But if you're using an impressed current system, there's the possibility or likelihood of generation of gases at the metal surfaces. At the anode, you can generate chlorine, again a toxic gas, and hydrogen at the cathode, at the steel surface, and this can generate obviously an explosive atmosphere. So vital to have adequate ventilation of the headspace and water exchange to avoid build-up. So just to finish off, next slide, please. Just to mention the issue of corrosion fatigue. This is probably the mechanism that will determine the life of the offshore wind structure. It's likely to be the fatigue life that causes the structure to be decommissioned, and fatigue, of course, is the phenomenon whereby a material can crack due to repeated cyclic load, but at a very low level, far below the material strength. But in the aggressive environments, you add in the aspect of corrosion, and you can enhance fatigue damage. So this corrosion fatigue is the combination of fatigue in a corrosive environment, especially seawater. And looking at the plot on the right-hand side, you can see if you're at a low stress range, let's say below 100 megapascals, the seawater free corrosion fatigue life is significantly less than the fatigue life in seawater with cathodic protection. So they're shown by the red and the green plots. And there's maybe almost an order of magnitude difference in the number of cycles shown on this SN curve. And so, if you've designed with CP applied and assumed maybe a 20-year design life, if the CP isn't adequate and you're getting free corrosion, then you might be at a fatigue life of maybe only a few years. So clearly it's important to have a detailed fatigue design for the structure with adequate corrosion protection. And just to finish off very quickly, a couple of slides on monitoring. We've talked about the application of mitigation to minimize corrosion. So if I could have the next slide. Then need to assess whether the mitigation options that have been applied are being successful. And there's several options for the monitoring. Perhaps the most commonly used exposure, weight loss coupons, and just put in a couple of images there of a retrieved sample, and then one after cleaning when the weight loss would be recorded. The corrosion products seen on the coupon are very valuable, and so the sample should be preserved, and laboratory analysis can help to determine what corrosion mechanism is occurring, and detailed analysis can look at rates of localized corrosion and attack. There are some other methods for direct corrosion measurement, electrochemical technique, linear polarization resistance, LPR, can be applied. So special probes are required, which would include a counter electrode, a working electrode, and a reference electrode. So a little bit more complex. There's also electrical resistance probes, whereby the resistance of an element changes as it corrodes, and they can give you specific corrosion rates for the environment. But of course, these two methods do need cable connections, and then there's manual monitoring or equipment for automatic data acquisition. So it's getting a bit more complex. And if CP is applied, it's obviously important to monitor the CP system as well, to look at the system output. If you've got an impressed current system, and you would typically measure the structure potential, and also you might, if you've got any coupons installed, look at current flow, so you can confirm the current density. And final slide, where there have been problems with the environment inside some of the early monopiles. There's monitoring, perhaps to look at the pH to check for acidification that might be carried out. If you're wanting to check whether your overall corrosion strategy with reduced oxygen has worked or not, clearly you need to be monitoring, to be measuring the dissolved oxygen content. And then there's other measurements such as electrical conductivity, just to provide levels of salinity are useful. And then if a more intensive investigation is required, that would maybe involve sample collection and chemical analysis and bacterial analysis to check what the corrosive environment actually is within that monopile. So that's a brief summary on the corrosion aspects. I'd now like to hand over to Paul at Apollo, who's going to cover the integrity management side of the document.
Hello, so I'll briefly cover some other specific component degradation issues, along with going into some key aspects of just general offshore wind integrity management. So this table brings together the key mechanical components located at the top of the tower and summarizes the degradation mechanisms that are known to affect them in offshore wind. The table may not be exhaustive, but the purpose here is to try provide a structured way of thinking about how the different systems and components degrade over time. The table is organized by system and then broken down into the individual components within those subsystems. And then across the top, it highlights the typical degradation mechanisms considered in the guideline, such as corrosion, fatigue, overheating, vibration, and wear. So what this table shows quite clearly is that there isn't a single dominant mechanism across all the components, and most items are actually exposed to multiple degradation processes, which is why a one-size-fits-all inspection or maintenance approach isn't correct and just won't work. The table also introduces example criticality categories, so A, B, and C. So this is where category A covers components where failure primarily impacts performance or availability, but doesn't immediately compromise the structural integrity or safety. Whereas category B would be components where failures can escalate into integrity issues if not addressed. So you've often got a limited time of continued operation, but with an increasing risk. And then category C would be where components whose failure could lead to like a catastrophic consequence. So that's like major structural damage or safety hazards or just a prolonged loss of operation. I'd stress that like these categories are sort of illustrative. So operators should really like sort of define their criticality in a way that reflects their own sort of operational, legal, and sort of like commercial obligations. But this is like a good reference for doing that. And yeah, the key takeaway from this is just understanding how components degrade and the consequences of failure is key to setting proportionate inspection, monitoring, and maintenance strategies, which then the later chapters of the document build on. So yeah, next slide, please. So this slide highlights a small number of component hotspots where experience shows degradation can develop quickly or have significant consequences if not managed effectively. So starting with blades, so the guidance does deliberately provide only limited detail here. Blade integrity is sort of highly specialized, so issues do require dedicated expertise and sort of a tailored management approach. But from what is included blades-wise, the key message is sort of emphasizing early detection and then escalation to specialist support. Transition pieces, sort of also a well-known integrity hotspot in offshore wind. So for grouted connections, one concern is the risk of like load distribution, redistribution, and movement, which can lead to sort of cracking, wear, and loss of stiffness if not identified early. Bolted connections, you've got the threat of like loss of preload, then fatigue, and also corrosion are sort of the recognized degradation mechanisms, and that sort of has a knock-on effect to the structural integrity. So yeah, for both of these sort of cases, the emphasis is on targeted inspection and monitoring to detect the early signs of degradations before you get into any significant issues. So yeah, just trying to look at the guidance is trying to focus attention on like known hotspots where like being proactive can reduce risk. Next slide, please. And so some of those issues I just spoke about are due to external drivers. So some of these that when assets are exposed to are so a combination of like met ocean loading, temperature variation, UV, marine growth, and seabed scour. So these are all sort of highly site specific. Conditions vary significantly by region. You've got water depth and seabed type. So degradation rates and mechanisms are not always uniform across a single field. Marine growth and scour can influence both the loading and corrosion behaviour, as well as just sort of providing issues for inspection, access issues for inspection. Sorry. Then we've also sort of highlighted potential accidental and unplanned damage. While these are generally low frequency events, they can have high consequences if they affect critical components. So yeah, these sort of events typically should trigger like reactive targeted inspections rather than waiting for like the next scheduled campaign. So yeah, it's just this slide was about just trying to account for both, trying to include both predictable and unplanned damage events within your integrity management. Next slide, please. So yeah, this slide sort of tries to set out why integrity management matters and what the guidance is trying to achieve. So it's just about being clear on what matters and what standard by defining things like your performance requirements. So everyone has the same understanding of what good looks like. And it just helps link inspection, monitoring, and maintenance activities sort of back to risk in like a consistent manner rather than sort of dealing with things in isolation. Yeah, it's not all about a big part of the guidance is about sort of governance and assurance. So the integrity management side isn't just about what's happening offshore, it's about having the right plans, competent people, good records, and like clear justifications for having to do things like deferrals or whatever actions you're undertaking, and just ensuring what you're doing is actually effective. So in terms of like how to do this, the document does set out like a integrity management framework based on like the operation stage of the life cycle. So yeah, I'll just go through that on the next slide, please. Yeah, so at the top of the framework, levels 1 to 3 are really about the governance. So these are the things that specifically matter to the company. So what the system is expected to do and how roles, responsibilities, and assurance are set up and maintained across the asset base. Level 4 and 5 are more practical elements. So this is where your strategies, guidelines, and procedures sit, covering areas like inspection, corrosion management, and your anomaly management. At the bottom, level 6 and 7, this is really the asset data, drawings, records, and the software tools that you use. So basically, like all the inputs and outputs of what everything else relies on, because if those aren't right, the rest of the system will struggle. So this framework is largely based on oil and gas experience, where formal integrity management systems are well established. However, it is acknowledged that offshore wind does have a very different safety risk profile, but the underlying ideas around the structure and traceability and assurance still sort of translate well into managing offshore wind. And we're not saying you have to implement every tier exactly as shown here. It's just about using the framework as a reference for what good looks like, and it can be scaled to the size and complexity of your own assets. Yeah, next slide, please. So here are 3 different approaches that are commonly used in offshore wind and how they tend to be applied in practice. So you've got fixed interval approaches, which are time-based, generally suited to the more predictable items and routine checks. Then you've got risk-based inspection, which takes a different approach, where the inspection scope and frequency are driven by likelihood and consequence, and then updated as you learn more about the asset. So this is typically more appropriate for your like primary structures, foundations, transition pieces, and the high consequence components. And then you've also got reliability-centered maintenance, and that's usually applied to the rotating or complex systems. So where failure modes are understood and condition data is available. So like, for example, the components in the drivetrain or like your pitch and yaw systems. And just a key point to note is you don't have to choose one to solely work with. In reality, it's the hybrid approach where the method used is selected based on the component criticality, how it degrades, and the availability and quality of data. Yeah, next slide, please. Yeah, so as previously mentioned, different components degrade in different ways. So inspection methods need to be sort of matched to what you're looking for, from primary structures to foundations, mechanical systems, and like right up to the blades. These techniques are sort of deployed using a variety of access methods: hands-on inspection using rope access, or remote technologies like drones and crawlers above water, or subsea, you've got ROVs and autonomous vehicles. So the guidance just sort of tries to highlight that the choice of technique and deployment method should consider factors such as the component criticality, any access restraints, and just like the general environmental conditions, as well as keeping like an eye on cost. Inspection is also sort of typically used alongside monitoring, which sort of helps track and flag changes in condition and performance over time. But then the inspections can then provide the detailed confirmation needed to understand the damage, and then you can decide on the right response. So yeah, the next slide gives a simple fatigue crack example to show why method selection matters. Yeah, next one, please. Yeah, so this slide's really about linking the inspection technique and how it's deployed to what you can actually detect in practice. So different techniques are better at finding different types and sizes of defects, and that directly influences how often you inspect and which methods are appropriate. So yeah, this graphic shows a simple fatigue crack example. So early on, when cracks are small or not yet surface breaking, the visual inspections won't pick them up. So you need a higher sensitivity inspection, such as like non-destructive testing or examination, would be needed if early detection is important, which is typically the case for like fatigue critical details, where like analysis shows like limited remaining life, or where like consequence of failure is high. The crack will eventually propagate to a size where it can be detected visually, but by that point you're much closer to fracture. So yeah, the key message is that inspection intervals and the method should be driven by how damage develops and then what your inspection can realistically detect. Yeah, next slide, please. So yeah, as sort of mentioned earlier, monitoring helps sort of track asset condition, the operational inputs, and environmental loading over time. So you're not just solely relying on like periodic inspections. So the overall aim with monitoring is to support integrity, safety, and operational reliability by spotting changes early and understanding how that asset is actually being loaded and used, which is sort of very important considering these are unmanned assets. So what's sort of shown on the slide here is a range of different monitoring types. I won't go through them just for time, but yeah, each of these provide a different part of the picture, and together they help explain why degradation is occurring, not just that it is. And yet, in practice, these systems aren't usually deployed in full across every turbine. We mentioned the concept of fleet leaders and the guidance, where enhanced monitoring is installed on a limited number of representative turbines, and which are then information can be inferred to the rest of the farm, and they're just typically selected based on location and exposure. So an example would be like turbines at the edge of a wind farm that experience higher turbulence or loading. Yeah, so I'll go on to the next slide. Just a couple more from me, and go through it quite quick. So yeah, this slide tries to introduce the preventative side of maintenance and repair, which is really about just trying to do the right work at the right time to avoid failures in the first place. So yeah, preventive maintenance, it sits like firmly within the integrity management framework as it's sort of planned, risk informed, and linked back to what matters for the asset. So yeah, there's some fairly typical examples shown on the slide here. I won't sort of go through them now, but what I will sort of highlight is the guideline also has like a strong emphasis on preventative planning. So spare part strategy is a good example. So considering your fleet size, failure rates, component criticality, and lead times, and then obsolescence is also flagged as a real risk. So yeah, next slide, please. Yeah, so this slide shifts on to corrective maintenance, which is more about responding when inspections or monitoring identifies issues more, or when failures occur. So the aim of corrective maintenance isn't just to fix things quickly, but it's to try and restore integrity and performance in a controlled and justified way. So again, there's like a few examples of physical tasks shown on the slide here. Just don't quite have time to go through, but what's important is the process shown on the right. The guidance is clear that the corrective work should follow a structured flow. So you've got your detection, then risk assessment, execution, and sort of validation stages. And whilst these are all important, I just want to say the last step is key in confirming the repair is effective through either reinspection or through reinspection, and that just to ensure that the risk is resolved and controlled. Yeah, and sorry for one last slide. That's on the next one. Yeah, so this final slide for me just touches briefly on life extension, where the guidance can be seen as more of like an introduction to the key considerations as assets approach the end of their original design life. So there's like an important distinction that's made is between offshore wind and oil and gas. So in wind, the life extension decisions are much more like influenced by like the size of the farm, the digital monitoring in place, and just component supportability going forward, rather than in oil and gas, it's more permanently manned installations, which can have like highly bespoke inspection programs. The document also highlights, as I said earlier, the key risk of obsolescence. So particularly for the control and electrical systems, which can become unsupported well before the primary structure physically reaches its end of life. So this just makes early engagement with OEMs and the supply chain especially important. And the main strategic options for life extension are also sort of introduced. So you can keep the asset as it is by just extending the life based on condition and data, or you can go down partial repowering to improve yield, but keeping your existing substructure. Or there's the full repowering, which is essentially reusing an existing site, but with more modern technology. That's, I was going through quite quick, but that's all from me, and I'll hand back to Gareth now.
Thanks, Paul. Right, in quick summary, and recognising that we have actually gone over time, as we've explained, the new Energy Institute guideline provides what we think is a comprehensive review of the different corrosion and degradation issues faced by the facilities, highlights the different environmental areas and options for material selection and corrosion control. As Paul's just summarised, provides overall integrity management issues, and highlights monitoring and inspection requirements. And as mentioned earlier, whilst the document is based very much on European experience, the guidance has been written aimed at a worldwide application, noting that each location, facility, and hence management plan is potentially unique. You've heard the phrase before, one size does not fit all. This is definitely the case for offshore wind. And with that, I think we finish, and hand back to you, Cameron.
Okay, thank you very much. We are slightly over time. Is everybody okay to hang on for a few minutes to answer a few? We've got some great questions in the question section. Are we okay to hang on for a little bit? Maybe answer a few of those before we close. Would that be okay, folks? Yeah. So Demetrius Evangelopoulos has asked the question. This is quite an interesting one. I think it might have been covered with some of the new standards that are out, but as we optimize designs and we look at higher strength steels, sort of S460 and above, the risk of hydrogen embrittlement becomes a major concern. Now, the question is if our guidance has balanced the requirement for aggressive cathodic protection potentials against the stricter voltage limits needed to prevent hydrogen cracking in these high-grade steels. So open that if anybody would like to field that one, or is that something that is covered with the new standards, etc., that's coming online? Who wants to take
okay, I'll answer that one. Yes, the standards do address hydrogen embrittlement issues associated with it. Now, of course, it depends what you mean by high strength steel. And actually, S460 is not, as far as I'm concerned, high strength. But the issues are very much that if you're using galvanic anodes or sacrificial anodes, as they used to be called, then for the normal type of those slightly elevated strength steels, the risk of hydrogen embrittlement is minimized by simply using galvanic anodes. If you're using an impressed current system, then yes, that does become a major concern, and is covered in both the ISO and the DMV guidance as to how to optimize that.
Perfect. Thanks very much, Gareth.
That question.
Next question we've got is, this is an anonymous one, but why is the buried side corrosion rate lesser than the atmospheric or splash zones corrosion rate? So who wants to take that?
Yeah, I could pick this one up. Yeah, so as I mentioned in the presentation, it's really controlled by oxygen. The corrosion rate is controlled by oxygen. So in the atmospheric and splash zones, there's a plentiful supply of oxygen to act as the cathodic reaction to drive the corrosion. But the corrosion rate is lower in the buried environment, largely because there's no oxygen present. It takes a long time for it to diffuse from the atmosphere, from the seawater down into the seabed mud. It's a very, very long path, and so there just isn't the cathodic reaction there to support corrosion. Just the one caveat on that is you can get higher rates of buried corrosion due to MIC in that top layer. If just to reiterate that. So, and of course, MIC can lead to quite high rates of attack.
Just to clarify for those who aren't into the jargon, that's microbiologically influenced corrosion, or bugs eating steel in the vernacular.
Apologies.
Thanks for keeping us right there, Gareth. That was excellent. Thanks, David. Now, Elizabeth Hickson has posed the question, if we covered structural bolted connections, if they're included, thinking of this rather than instead of grouted connections, did we actually cover bolted connections? There is separate EI guidance on bolted joints. I would just flag that, but did we specifically cover that in this guidance? I'm trying to remember.
For Paul, I think.
Yeah, so it's sort of touched on. I wouldn't say it goes into like great detail, and I think it does actually reference the document you've just mentioned, Cameron. But yeah, other than sort of what I said in the slides, I don't think there's much.
I can answer. There's a surprising amount of references scattered through the documents, particularly around the higher grades and the use of corrosion-resistant alloys, but no specifics on structural jointing details.
Thanks very much, Donald. Donald also from Apollo joining in there to help with that question. Not just introduce you. So, okay, we've got another question here from Demetrius Evangelopoulos. Looking at floating substructures, this is interesting in the floating area. Dynamic interaction of mooring chains creates wear zones that strip coatings much faster on fixed assets. So we're being asked here, do you recommend over-designing the ICCP, the compressed current capacity, to compensate for this accelerated breakdown, or are we seeing a push for entirely new abrasion-resistant coating standards for these dynamic zones? I think this is very much in the developing part of the business. Any thoughts on that, folks?
Yeah, I'll take that one. Obviously, as we mentioned before, the floating structures is a topic which has just started, and we're just getting together the outline issue. And the aspect of mooring and mooring interaction onto the floating structures is an issue that would be has already been flagged and will be addressed in the new document. I think there's two separate issues here. First off, it comes down to the design of the mooring chain interaction to the structure and designing the layout, so minimizing the risk of wear in the first place. But then in terms of over-designing the ICC capacity, that's a slight misnomer. What you would do is make sure you allow for excessive wear of the coating in the area of the interaction with the mooring and take it that way, which is not in itself an over-design of the impressed current system. It is just ensuring that the CP will be sufficient, allowing for potential wear in due course.
Perfect, thank you. Alistair, did you add
anything? I can add that on the FPSO, the floating oil structures, they tend to have like a trumpet shape at the chain interface, and the trumpet shape seems to matter. And simple things like avoiding hard spots due to welds in the zone. So they do get worn. They do get worn away, but they don't actually seem to be a major problem.
All right, thank you, Donald. Alistair, did you want to add anything in there, or is that income?
No, nothing more than from a technical side from what Gareth and Donald have added. But I would just like to emphasise this is the first edition of this guidance document, and as with all other EI documents, it is subject to a review. And I think it's around 5 years is the review period, although I suppose if technology does advance at a hell of a rate or not, then we could bring that forward. And I would suggest that some of these questions are absolutely fantastic, and hopefully I can allay some concerns. This is the first edition of the fixed offshore. Floating offshore is, as touched on earlier, is our next project, which will be published in maybe a couple of years' time. But both of these will be reviewed periodically following that, and with more emphasis perhaps on the more pressing and prescient corrosion and asset integrity management issues that are there in the future, and indeed high strength steels and HIC or SOHIC and others shall be addressed as appropriate. There is precedence for this in the dirty old industry of oil and gas. We had the guidance for corrosion management in oil and gas production and processing. That's in its second edition. The second edition is now about 5 or 6 years old, so I suppose we'll be looking to review that again. But one of the important things is it is a de facto standard and how to do things, and so that's what we would aim, I would suggest, for our second edition documents, that they become the de facto standard for this industry. Clearly, getting everything together at once and given the pace of change, we would probably never be in a position to publish if we continue to do that. So there is a line being drawn in the sand for this edition, but I dare say the next edition will be significantly more niche, as some of the questions have inferred. Thank you.
Thank you very much, Charles. That's a beautiful summary. Right, we are well over time. There are a number of questions. We're not going to get through them all. I would welcome anybody whose question isn't answered to get in touch with me, and we would look to field that question offline. But if I say we'll finish at 1:15, maybe time for one more, if that's okay. And there's a question here from Nathan. Does the guidance cover any recommendations when considering the impact of global warming on corrosion or life extension, i.e. the environmental conditions are changing and the design is based on historical data? There's a question, folks. Anyone want to take that one?
Yeah, I'll take that one.
Oh, here we go. There's Gareth.
Yeah, the issue of changing conditions is mentioned in the document. I wouldn't say we give any specific recommendations because we're looking into the future, and in terms of exactly how global warming will affect conditions is still unsure, shall we say. The main issue, of course, is that any design going forward has to be based on the conditions you're expecting. So consequently, the typical temperatures for the seawater or the atmosphere, the flow conditions, change in salinity, change in dissolved oxygen levels, which of course is a function of salinity and temperature, all have to be taken into account in design. So this is an area which I know the various cathodic protection standard committees, both in ISO, Euronorm, and what was NACE, etc., are looking at in terms of sustainability and applicability going forward. But this is very much a watch this space aspect.
Thanks very much, Gareth.
There is also your environmental group is studying this, Cameron, because it's an active issue for the North Sea existing oil and gas assets, and that the Met-Ocean data hindcast isn't always accurate.
Absolutely, Donald.
There is work in the background going on, I think, is the answer.
Yeah, I did mention at the start there was a whole separate part looking at the effect of the environment, the Met-Ocean data. But right, folks, we're just about 1:15. The questions are still coming in. So, but what I suggest is that we maybe bring that to. Let me just make sure I've done it. Yes, I've done that one. That's perfect. If your question wasn't answered, please get in touch, and I'm sure we can field those questions for you offline. But for now, we're at 1:15. We've slightly overshot our time. I would just like to say many thanks to my fellow panelists. That was absolutely fantastic. Really enjoyed that. It was great going through that in detail. I'd also like to thank all of you that joined us on this webinar. I hope you found it useful. Judging by the questions, which were fantastic, by the way, it's clear this is put a lot of interest out there. The guidance is published. Please go and have a look at that, and you can see about getting access to that kind of thing. But just to say for now, I think we have given that guidance a good introduction to yourselves out there in the wide world, and I hope you have enjoyed today as well as finding it informative. But my last thanks is to my colleague Amy, who has kept us right, kept everything moving beautifully in the background, and made sure we did a good job on this. So that, I think, is us. I think if we bring this to a close, just for me to say many thanks to everybody that's participated today, and I look forward to joining you all in a future one of these in the future. Many thanks indeed. Take care.
Thank you.
Cheers.